So last session we stopped here with performers. Actually, we covered attention mechanism, and then we said attention mechanism has its own drawbacks, which is the cost of attention in the sequence length is going to end up being quadratic in the sequence length. And then we tried to address that problem using three different methodology. One of them was reformer, which was based on the idea of the softmax being dominated by its largest element. And therefore, you don't need to work with all of the keys, but you need to work with the keys that are going to end up in the same bucket as your query, according to some hashing function. That way, you're going to reduce the cost. Another idea was don't compute Q times K, do it individually. Look at your queries individually, one after another. And that way, you're going to reduce the memory. So one is reducing the memory, the other one is reducing the cost. Then we introduced another idea, which was turning transformers back into RNNs. And the idea was dividing this bivariate function into two components that are single variate. And as soon as you do that, you can compute, just rearrange the furniture a little bit, and then compute most of your terms once and just reuse them. That's for the encoder part of your transformer. For the decoder, that's going to give you the recurrent neural network that you're actually looking for. And it was all based on this idea. Don't compute Q times K and then multiply by V. Multiply K by V first and then multiply by Q. And that's the way that you're reducing the cost to be linear. And to be able to do so, you need to have a kernel that actually decomposes into two components, Q and K. Otherwise, you cannot do this trick. And we did the same thing in another approach, which was performers. And the only thing that you're doing here, the big idea is the same. You still have query key and the value. Rather than computing query times key first and then multiplying by V, you are gonna multiply K by V and then multiply the result by Q. So that's the same idea. To be able to do so, you need to have your kernel, your softmax kernel to decompose. Previously, you were using this ELU function +1. Here you are borrowing ideas from positive random features, which is that you can decompose your kernel by keeping sampling from a normal distribution and then multiplying two univariate functions together. But in terms of big picture, you have key times value. You compute that operation first and then multiply by the query. Any questions about performance? Things were a little bit more difficult when it came to the unidirectional case. And this is when you're actually decoding the decoder part of a transformer. But if you think about it, this one is also very similar to the previous paper, where you had this recursive nature, giving you back RNNs. It's the same thing here. The prefix sum idea is you're going to do your summation up until a point, and then you're going to add the other time step to it. And it's going to turn into a recurrent neural network, even this one. Mathematically, it looks more complicated or complex looking, but the big idea is simple. Any questions about performers? Was everything clear? Okay, cool. With that, we can close the chapter of translation. We learned a lot from translation. We learned how to actually turn a sequence or turn a sentence and tokenize it, turn it into a sequence of integers. We learned about byte pair encoding. We learned about word piece. We learned about byte level byte pair encoding. We learned about sentence piece. And then we learned about a unigram language model. The other thing that we learned about was the attention mechanism and how you can actually improve upon it in terms of performance. With that, we are ready to go and do language modeling.